This is video 6 using I2C and a small OLED display on an STM32 MicroPython and the black pill. The code for this video is at the GitHub site. These videos on MicroPython on the black pill should work as well on any STM32 F4 board. All code examples have pin definitions at the beginning of the file to allow the user to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. Inter-Integrated Circuit, I2C, is an interface for communication between a master and one or more slave devices. I2C consists of two signals, SDA and SCL. Each device uses a specific address. The signal lines will not need pull-up resistors, as the OLED device includes these. Certainly, MicroPython I2C driver handles the complexity of the I2C protocol, as we shall soon see. On the black pill pinout diagram, the I2C pins are mostly on the left side and are the color light blue. The black pill has 3 I2C ports available. Since we need some pins for other functions, we will only use the I2C1 port at PB6 and PB7. Fortunately, an I2C port can communicate to multiple devices. The README on GitHub provides suggestions on how to purchase an OLED. In this video, we use a small 0.96-inch OLED display that is 128 by 64 pixels that I purchased from Amazon. To keep the graphics simple, it displays black or white pixels. In our case, instead of white pixels, we get the upper pixels displayed yellow and the bottom blue. The small OLED can be inserted directly into the port, ensuring the signals on the PCB and device match. Now, open the file scan_machine_I2C in Thony. Let's look at the code. This is a test script to scan the I2C bus for any connected devices. The code begins by invoking an import of the pin soft I2C from machine. The third import loads the time library. Now we define the I2C pins and the user button. Next, we set up the I2C variable and assign it the I2C function using the defined pins. Finally, the program's main code waits for the user button and performs a scan. Let's run the program. As you can see, the program prints the decimal and hex values of a device's address. In this case, it prints the address of the OLED. Now that we know the OLED is connected properly, let's try it. The first thing we need is to load the graphics driver. Disconnect the black pill from your desktop and reconnect it. When you do that, the desktop opens a USB drive. Drag the file SSD1306.py driver file to the drive. This is the graphics driver. Now, open the file bb_small_09606 OLED_machine_I2C1 pi in Thony. Let's look at the code. The code lights the display. This script waits for the user button, then displays text on the OLED. Let's click the green run icon to invoke the program. The OLED screen is 128 by 64 pixels in black and white, white being yellow or blue. The OLED text displays a string starting at column 0 and row 0. The default font is essentially 8 pixels wide and 8 pixels long, meaning we can fit a maximum of 16 characters across the OLED in 8 rows. We see three functions: the OLED.fill 0, which clears the screen to black because 0 is black. 1 would clear the screen to white. The OLED text screen, which sends a string at a certain column and row, and this is the starting pixel, so it's going to be 8 characters wide, so you'll see the next row is 8 pixels away. And the OLED show, which lights the pixels. It's important to remember that none of these commands will display until the program enacts the show function. In the next video, we will learn more about the OLED to display graphics. You can also check the standard MicroPython documentation for additional commands. Thank you.